Hello friend, welcome to Engineer. In this video we see the analysis of beam by using preliminary stiffness method. So this is the question given, that is the 80 kN point load is acting between A and C, and the UDL and this point load is acting between C and E. So let us start. For solving this method, so there are 5 steps. So we go by step, that is this is our first step, that is to find out the degree of freedom and represent as the matrix D. I here considered the point A, C and E as my nodal point. So here the degree of freedom is C, that is the displacement at A, displacement at C and displacement at E. I represent this in this matrix form, that is theta A, theta C and theta E. I represent for just easiness or for our convenience, that is D1, D2 and D3. So it is nothing but the displacement matrix. Now moving towards our second step, that is the stiffness matrix S. So how to calculate the stiffness matrix? First of all, you have to know how to calculate the stiffness. I give you the formulas of stiffness in my last video. For details, please see my last video. In that I mentioned how to calculate the stiffness there. So here we directly calculate this. So for calculating the stiffness matrix for deflection at A, apply D1, that is the theta is nothing but the A. As we know, stiffness is nothing but the movement produced due to unit deflection. Stiffness is nothing but the movement produced due to the unit deflection. That's why apply the unit deflection, that is D1 equals to 1 in release resistance structure, in this structure, and we are able to calculate the stiffness at A. So I just represent here, that is S11, S21 and S31 as the movement at A due to unit deflection, movement at C and the movement at E due to unit deflection at A. So here I calculate directly, that is S11 is nothing but the 4EI by L. So how this formula is come, please refer my last video. So here I directly use that formula, that is S11 is nothing but the 4EI by L. Directly put the value, we get 0.5 EI. Here S21 is 2EI by L, S21 is 2EI by L, and here for C to E, no deflection is acting, that's why stiffness is 0, theta 0, that's why stiffness 0. So X21 is directly calculated as 2EI by L, which is 0.25 EI, and the S31 is nothing but the 0. For calculating the stiffness due to the unit deflection at C, I mentioned S21, S22, S33. As we have to generate the stiffness matrix for the each degree of freedom, that's why. So this is first column. Now we are in the second column, that is S21, S22, S32. As movement at S12 is nothing but the movement at A, S22 is nothing but the movement at C, and S32 is nothing but the movement at E due to unit deflection at C. Okay, so here I represent unit deflection. As we considered here, the clockwise sign as positive, that is unit deflection at C is here the clockwise for AC span and here clockwise for CE span. So the stiffness here are S12, means the stiffness from A to C is 2 EI by L, so we directly get 0.25 EI. The stiffness at point C is the summation of S22 dash plus S22 double dash. For this span, that is for C to A, the stiffness is 4 EI by L, and for C to E it is 4 EI by L. Here I present 2 EI just because of here given the 2 EI. That's why 4 in bracket 2 EI by L. L is nothing but 7. So it is distance between these 2 points. So directly get 1.643 EI for S22, and S3 is nothing but the 2 in bracket 2 EI by L, which is 0.57 EI. For the third column, that is apply D3 equals to Z1, that is the theta I equals to 1 in the release distance structure. Here I mentioned here the theta E, that is DE, here theta E equals to 1. So this is nothing but the movements due to unit deflection. So here S1 3, S2 3, S3 3. So we know that S1 3 is 0 as the no deflection occurs here in span A to C. S2 3 is nothing but summation of these two, but in this span AC no deflection is occurred. That's why the S2 3 dash is 0 and S2 3 double dash is twice of EI by L, which is 0.571 EI, and the S33 is 4 EI by L, which is 1.143 EI. What the value we calculated here from this step to this step, that is first column, second column, and the third column, I represent all the values here, that is in the stiffness matrix. Now moving towards our fourth step, that is the calculation of load. As the method is called preliminary stiffness method, so here I calculate the load matrix, which is represented R minus R, where the R is nothing but the actual joint load, means the load acting at a joint, and RF is nothing but the fixed end reaction component with respect to both R and R with respect to degree of freedom. If the R 0 0 0, why? Because R is nothing but the actual joint load, and in our question there is no load is acting at a joint. No load at joint A, no load at joint C, and no load at joint C. Hence why all this with respect to degree of freedom is 0 0 0, and RF is nothing but the fixed end reaction component, which I represent here the MA, MC and ME. So here I calculate MA is nothing but the P L by 8, because here only the point load is acting, that is we know the preventing moment of this, that is P L by 8. So here I represent what I represent here, P L by 8, P is load, L is the length and 8. So we get minus 80 kN. MC is nothing but the summation of moment due to this loading and due to this loading. So that's why 80 PL by 8 minus P A B square by L square and minus W L square by 12. So here we get the minus 91.48, and the ME here, that is P A B square by L square plus W L square by 12, which is we get 159.23 as ME. So just represent in this matrix form, that is RF is minus 80 minus 91.48 and 159.23. As we have to calculate the load matrix, that is R minus RF. So here R minus RF is 80, 91.48 and minus 159.23. This is our load matrix. So what is the equilibrium equation? Equilibrium equation is nothing but the load equals to stiffness into deflection. As we know, load, this is R minus RF is nothing but the load matrix, S is the stiffness matrix, and D is the deflection matrix. So just represent here, stiffness matrix is what we calculated here, T deflections, and these are the loads. So just solve this matrix. As there are many methods for solving this type of matrix, we are also able to calculate this type of matrix directly by using our calc, but I solve this as the row. So this is row multiplication. That's here I need R2 is replaced by, that is row, second row. This matrix is represented by replace. So R2 is replaced by R2 minus 0.25 by 0.5 into R1. Here I have to convert this element into 0 for calculation of this displacement. So it is nothing but the row. Here I just want to do the row operations. So here I do this, that is R2 is replaced with R2 minus 0.25 by 0.5 into R1. So I get this matrix here. Just guys, you check it this by solving in your calc. And second row operation is R3, and R3 is replaced with R3 minus 0.57 upon 1.518 into R2, just to make the zeros at these places. Just convert this lower triangular matrix into 0. So if we convert in this type, we directly able to calculate the displacement. That is D3 is nothing but the minus 178.56 upon 0.92 0.929 EI. So here we calculate the D3 equals to minus 192.21 by EI. Similarly this we are able to calculate the D2 and the D1. So which is we get 106.61 by EI, and D1 is nothing but 106.604 EI. So this is our last step, that is the end moment. Here we are calculate, this is nothing but the soft deflection, that is MABC is nothing but this is the MBA plus twice of 2 EI by L in bracket 2 theta A plus theta C. Just represent this value minus P L by 8 plus 2 EI by L plus 2 into theta A. Theta A we calculated here 106.604 EI plus theta C. Theta C is calculated 106.6. So just by directly putting all this value we get minus 0.046, the movement from A to C. Next, the movement from C to A is PL by 8 plus 2 EI by L in bracket twice of theta C plus theta A. So just by directly putting all these value we get 159.956, which is MCA. Now the movement at C to E is minus PAB square by L square minus WL square by 12 plus 2 EI by L, but in this point C to E, EI is 2 EI given, that's why 4 EI by L in bracket twice of theta C plus theta E. So theta C is 106.61 and the theta E is nothing but a minus 192.31. So we get minus 159.47. So these two will be similar, and the minus the movement at E to C is PAB square by L square plus WL square by 12 plus 4EI by L twice of theta E plus theta C. So we get 0.486 kN. Thank you.